Okay, well, hello everybody again. I am very happy to be here in this online meeting, or join this online meeting with all of you. And I'm going to present a brief summary of our result from a study, the infrared emission in a sample of nearby quasars using CANARICAM photometric and spectroscopy data, and also recently photometric data at near infrared from EMIR and CIRCE, all of these instruments on CANARICAM, on Gran Telescopio CANARIAS. And these are my collaborators, the collaborators that have participated in all these investigations, and I have highlighted those that are present in this meeting. So our study has been divided in two topics. One, the inner star formation of quasars, and the properties of the dusty torus of quasar. In the first one, we try to answer this couple of questions. Is there a grand design circumnuclear ring like those present in Spitzer galaxies at easily detectable scale? And for those quasars with clear path polycyclic aromatic hydrocarbon features detected in the Spitzer spectrum, are these originated in the inner few hundred parsec or on kiloparsec scale? And in the second topic, we are trying to understand what are the physical and geometrical properties of the putative dusty torus. I prefer to say the dusty, the AGNs are surrounding dust. Because always we are writing this result, dusty, this, nowadays is very complicated to decide. So recently in a first work in 2017, we analyzed this infrared emission using only the NCOVA clumpy models. And recently we are using not only clumpy model from NCOVA, also the two-phase model media from Stalewski et al., and also smooth models and the disk plus GWIM models. So the samples are 20 quasars with a redshift less than 0.1, selected, limited by the flux at end band, because these objects were selected to be observed or to be detected with CANARICAM, and they have a hard X-ray flux larger than 10 to the 43 erg per second. And they have been observed, the 90% of them at mid-infrared C2 band, the 65% of them have the high angular resolution spectrum from CANARICAM at end band, and we recently obtained a near infrared high angular resolution image at H and K band for the 60% of them, and we are also used ancillary data from VISIR, for example, on VLT, and also the Spitzer spectrum. So we started all this work analyzing the mid-infrared high angular resolution image of quasar and looking for extended for circumnuclear rings. But we found that in most of them, the mid-infrared emission is unresolved. However, when we analyze the high angular resolution spectrum, we observe that in some individual spectrum, there is the path at 11.3 microns. And in the stack spectrum of these quasars, the path is clearly detected on this physical scale, less than 700 parsec and between 0.7 and 1 kiloparsec. So we measure we estimate the star formation, the inner star formation rate in these quasars using this calibrator, and compare with the star formation rate at a larger scale estimated from the Spitzer spectrum, and found that they are comparable, and we think that it is likely that the star formation activity in quasars is mainly concentrated within the central kiloparsec. We also estimate the black hole accretion rate and compare with the inner and larger scale star formation rate because the simulation from Hopkins and Quattire predict a correlation between these two quantities at different distances from the supermassive black hole. And we found that the star formation rate measured on the stack spectrum on a scale between 0.1 and 1 kiloparsec are comparable or is in agreement with simulation, but the star formation rate measured on larger scale, on few kiloparsec scale, is lower than predicted by simulation. Then we discussed this result in terms of 3 possible scenarios. One is that the quasar evolutionary state is not well accounted for in the simulations. 2, the star formation efficiency in the host of quasar could be quenched, and or paths in quasar are not effectively tracing the star formation within the few kiloparsecs. In the second point, in 2017, we published this paper in which we used the near infrared high angular resolution data from NICMOS plus the starboard subtracted Spitzer spectrum to constrain the 6 free parameters from the Klumpy-Dostie torus model of Rincova. We combine the parameters, the derivative from each quasar, and produce a global distribution for each parameter, and we compare these parameters with the parameters, the global parameters for obtained for CIFER-1 and CIFER-2 galaxies. And from this comparison between the parameters of quasar and CIFER, we found that the properties of quasar are intrinsically different from the properties derived for CIFER galaxies. And I highlight 2 main conclusions from this work: the combination of the angular width, the number of clothes, and the given angle result in escape probabilities larger than 5%, which is consistent with the classification of this object with like type 1 AGN. And the lower number of clouds and the steeper radial distribution and less optically thin clouds in quasar can be interpreted as dusty structures that have been partially evaporated and piled up by the higher intensity radiation field in these quasars, as proposed by Riset torus model. However, from this work, we also note and highlight that some parameters seems to be very degenerated, like the number of clothes and the index of the radial distribution. And this could be probably because we didn't have near infrared data for all quasars. And we also highlight that in some cases, the near infrared emission from HST was above the best fitted model. So we decided to obtain new near high angular resolution data from the instrument from the same telescope to build a well-sampled near plus mid infrared high angular resolution data. So recently, now this is the new image from near infrared H band, and we are subtracting from near after normalize the accretion diff to the UV data from galaxies. We remove the accretion diff from the near infrared data from at near and mid infrared data, and then we are using this accretion subtracted infrared data to constrain the smooth Klumpy's models and these plus outflow models. And recently, this is very preliminary, seems that models or data are better fitted by these plus wind models. And this could be consistent with a previous result in which we found that a high luminosity, these plus wind models better fit the spectral, the AGN dominated Spitzer spectrum in a sample of AGN where the silicate emission feature is very strong. But, well, we are working on that. So our conclusions, quasars are unresolved and near and mid infrared, and the star formation activity is present in the most nearby quasar, a scale of hundreds of parsecs, and the starburst activity in quasar is more centrally concentrated, and it is still not clear is this starburst regions are surviving to the strong radiation of the AGN. And we hope that the new NIR and MIR well-sampled spectral energy distribution will allow us to investigate which model better reproduce simultaneously the NIR and MIR data, and which make some conclusion about that. So thank you.
Okay, thank you. So we have the time for just one short question. So from Yana, how you estimate the 11.3 pH luminosity? How do you decompose the spectra?
Sorry?
To estimate the 11.3 pH luminosity, how do you decompose the spectra?
It's talking about the past luminosity in this here. This, I got it, the question, sorry.
Yeah, to estimate the 11.3 pH luminosity, how do you decompose the spectrum?
Well, we didn't decompose the spectrum to measure the path, the inner path the inner star formation rate. We measure the inner star formation rate is measured directly from the high angular resolution spectrum, which is extracted from a nuclear region of less than 1 kiloparsec, from some hundred of parsec.